Okay, so we now begin the discussion on the last lecture of this course, which is on unsupervised learning. A lot of the material is heavily borrowed from Kevin Murphy's excellent book, which you can use as a reference. So, unsupervised learning is very different from supervised learning in the sense that you're just given the output data without any inputs. And the goal is to then discover some interesting structure in the data, which is also commonly known as knowledge discovery. A very important conference in this field is called KDD, where the KD part is the knowledge discovery aspect. And unsupervised learning is inherently important because it is really difficult to get a lot of label data. Labeling is expensive, it requires sometimes human annotators, it sometimes requires very expensive sensing, etc. So, thus, unsupervised learning in its own is a really important problem to solve. And as we've discussed, we're not really told what is the desired output for each input. For example, when we're talking about classification, so we have an input set of features, which could be a feature vector. Let's say if you want to classify a fruit, and the features could be the color or the size of the fruit, and the output, what we're trying to predict is what kind of a fruit is this. But that is supervised learning where there is an element of supervision. But that is not the case with unsupervised learning, where the data set would be only consisting of features like the color of the fruit and the size of the fruit, etc. There is no output label given. So just given this data, we want to discover some interesting structure in the data, or to discover some patterns which we could then leverage and then accordingly utilize. In just a few minutes, we'll look at some applications which are enabled by unsupervised learning. And if you have to mathematically differentiate unsupervised learning with supervised learning, the first thing which we need to note is that we're given the data, the feature vectors xi, where I is the ith sample, and this is the vector. So this could be the length of the fruit or the size of or the color of the fruit, so on and so forth. Theta is the parameter vector, and all we want to do in this task is to build probability models of the form which model the probability of the features given the data or given the set of parameters. But if we look at the comparison between supervised and unsupervised, the first thing which we should note is that in the case of supervised learning, corresponding to each xi, there was the output label yi. And thus, we were trying to model the probability of the output variable given the input and the set of parameters theta. But unlike supervised learning, for unsupervised learning, we directly want to, or we just want to model probability of the input features given the parameters theta. For the supervised learning, this term is a conditional density. We're talking about probability density functions. So this is a conditional density, and for unsupervised, we just call it the unconditional density because there is no yi term here. So in some sense, unsupervised becomes a much harder problem to solve. If you look at this particular expression, which is probability of xi given theta. Now xi is not univariate. Like it can be univariate, but in many cases you will have the data across multiple dimensions. So now you have to model multivariate probability distributions, which is not as trivial as for the case of supervised. If you remember what we did for linear regression, for example. So there we wrote this term as probability of yi given xi comma theta is yi is distributed normally with the mean xi transpose theta and a variance sigma squared, right? So that's how we can trivially write those expressions. The important reason being that yi is a univariate, so you just need a univariate probability model. Of course, the input to that model can be multivariate. Xi is not a univariate, need not be univariate. So there are various applications or various sub-problems in unsupervised learning. We'll look at a few of them now. The most popular one is clustering. So you might have heard about the term cluster when you're talking about stars. So you say this is a cluster of stars. There are various constellations and so on and so forth. So let's look at this particular data now. This is now a two-dimensional data of a set of people with their height mentioned on the x-axis and the weight mentioned on the y-axis. And this is just a scatter plot. And on the right hand side, we have tried to divide this whole set of population into two groups or two clusters. If you if you look at these clusters, you'll probably identify that. So the right hand side shows two clusters. These are the people who are taller and who have more weight, and then these are the people who are shorter and who have lesser weight. So if you're able to identify such patterns, maybe you can design clothes for them, so you understand the market better, that what is the distribution of people, how many people belong to each, let's say, clothing size, or you could also build certain other, let's say, medicines for them, let's say. And if you were to change the number of clusters, you could also look at some interesting, so this data can also lead you to some further interesting insights. You might have people who are shorter but are overweight. You might have people who are tall but are underweight. So these sort of clusters would be also pretty important to identify. And these groupings can be identified without having any label as such assigned to them. So what you just see is a red cluster and a blue cluster, but there is no as such labeling done. So you as a human being have to interpret the clusters on your own. As we discussed, the blue cluster is probably taller people with more weight. The red cluster is probably shorter people with less weight. So just to revise, the key idea of clustering is to divide the data into groups or clusters. And if we assume that there are k clusters, we have two goals. So you might already be wondering that how do you learn k, or how do you know what k to use, k number of clusters to use? So that's the first problem. We are trying to estimate the distribution over the number of clusters, which is to say that you're modeling the probability of the number of clusters given data. And then finally, you'll choose the mode of this, or you'll maximize this term to get a k optimum. And secondly, then you want to estimate which cluster each point belongs to. So let's say in this case, we have k equal to 2. So, and this is the point x1, let's say. You want to see whether x1 belongs to red or blue. So either one of the two classes, or two clusters, sorry, not classes. So there are two important goals. First, distribution of the number of clusters. Second, which cluster does each point belong to. Now in the traditional machine learning, when this sort of topic is introduced, you'll generally see data in two-dimensional, etc. for clustering, but clustering can be done on any number of dimensions. And let's look at a different application now. Now this is showing the energy usage of a lot of homes in a certain region, and basically you have hourly reading for them. So every hour you have 1 point, and you have plotted the energy across a lot of homes. You can of course see some dominant patterns, that during the night hours, most of the homes have low energy consumption. For most of the homes, the energy consumption increases during the morning hours. That is when they're preparing breakfast, and the energy consumption is also higher in the night when people come back from offices, right? So the idea is now you have a 24-dimensional vector. Xi belongs to R24, and you have, let's say, 47 months and I don't know, a lot of homes. So you want to then cluster these homes, or you want to find certain groups of homes. So again, the idea is, let's say you're an energy discom, and you want to identify different kinds of customers, and you want to build them, or you want to give them some custom solutions. You want to identify, are there homes which have peak energy usage at certain times of the day? Can you give them some incentives so that the grid is more stable? There can be numerous such applications enabled by this technique. And now we look at these different clusters. So the clusters are now shown in the 24-dimensional space. And you can very clearly see that for all the clusters, the energy consumption in the night is fairly low. But then you see different patterns. So we look at, let's say, the red cluster, whose energy consumption rises very mildly during the morning hours and then again falls. So these may be homes which have, so probably smaller homes that have very few appliances and very few people. So the energy consumption is largely low. The green cluster may be people who rise late. So if you see that the energy consumption is peaks significantly, but it is generally low compared to the other clusters during the early morning hours. And these folks probably spend their entire day at home, because if you see that the energy consumption keeps on increasing and does not decrease, so probably they don't go to the office. Whereas the blue cluster looks like they go to the office, come back and turn on the air conditioning, etc. So this was just to show that clustering is not only limited to low number of dimensions, and you'll have to think of novel ways in which you want to visualize this data. The other category of unsupervised algorithms is dimensionality reduction. Now, this becomes extremely important because you have already now studied that many machine learning models suffer from what is known as the curse of dimensionality. If you have more dimensions, you require exponentially more data to be able to do a good job, specifically when you're looking at nearest neighbor like methods. There, the definition of distance becomes very complicated if you don't have enough, or it becomes ambiguous if you don't have enough data in high dimensional space. So there is another class of unsupervised algorithms called dimensionality reduction. So if you look at this particular data, it's currently plotted on a two-dimensional line. But can you think of a single dimension which would be enough to represent this entire data? Before that, let me just define dimensionality reduction. That is, you want to project the data to a lower dimensional subspace, which is going to capture the essence of the data. And this word essence is really important. You want to be able to capture the important characteristics of the data. If you lose the essence, then projecting to a low dimensional subspace is of no consequence, of no use. And the motivation behind projecting to a low dimensional space is that while the data could be high dimensional, but there are only a small number of factors which are really important. So think of it as you're building a model to predict, let's say, the weather in your city for tomorrow. Now you could throw in a gazillions of parameters and you could predict using some complicated model. But out of those, let's say it's only 5 or 6 important parameters. I'm not really talking about feature selection here, but I'm talking about, let's say, if we could project the entire data to a low dimensional subspace, which is some of which could be even transformations of the current features. So this is where feature selection is different from PCA. So for example, for feature selection, if I were to say you that you have to select some features. You have one feature X, you have one feature X1 and X2. You might say that let's just use X1 and then project the data, just look at the X1 values for each of the points. Or you could just look at the X2 values of each of these. So this is how feature selection would occur. But what I've shown here is a different dimension. So now you consider this 1D line, which is shown in this dark blue plot. Now this is, in some sense, you have transformed the data to a different space where the data's essence is captured. Right? So this is not feature selection in the traditional sense. This is just transformation of data to a low dimensional subspace. Now if you remember, this is somewhat or exactly opposite of what we were doing in the SVMs when we were projecting the data to a high dimensional subspace. Here we are projecting it to a low dimensional subspace. We won't go into details of dimensionality reduction in this lecture. And then you can also apply dimensionality reduction to very beautifully visualize your data. This is often important to understand some characteristics of the data. And this is a 2D visualization of the MNIST data where you have these different digits. This is done using TSNE algorithm, and you can see that you've basically projected what was 32 cross 32 uh, numbers or 784 size vectors into two-dimensional subspace, and you can still see that you're able to distinguish between these different set of digits. The other category of unsupervised algorithm, which is very important, is matrix completion. And for the first case, we look at collaborative filtering. Now, this is used for making predictions in the case when matrices have some values, but majority of the values in matrix are empty, and generally used in the case for recommender systems. So, for example, if you're watching, there is a very large population of users and the movies that they watch. So on the rows you could have movies, on the columns you could have users, and think of it as the Netflix data. So you would have probably watched a very small number of movies, and that would be true for almost all the set of users, but Netflix wants to recommend you what movie to watch. So they'll basically want to recommend you the movies for which they'll estimate your rating to be high. The cell values are the ratings on a scale of 1 to 5, 5 being highest, right? So you'll have a lot of these unknown values question mark. You want to estimate those using this given matrix. So one way to do this is to, again, assume that so as we said that we can discover some, so we said that we can discover some interesting structure in the data. That's the aim of unsupervised learning. And in matrix completion for recommender system problem, let's try to fix a structure. So we'll say that most of the movies, we'll say that the movies can be described using only a small number of factors or variables. Similarly, users have some affinity towards each of these factors. So let's think about a few factors which a movie could be described using. So one could be the genre, action or drama or comedy. One could be the length of the movie. One could be, let's say, the movie type. Is it Bollywood? Is it Hollywood? Is it some other wood? Right. So, and it could be, is it produced by a popular director, which could be a binary feature. So they could think of many such features. And each of the user has some affinity, or they have some importance that they'll give to each of these features. For example, I could be, let's say if I like just action movies, so my value for action would be, my rating for action movies would be very high, whereas for other movies would be low. My value for, let's say, Hollywood is high compared to Bollywood, and my value for shorter films is better. So corresponding to each user and the movie matrix the movie features that we've described, they can be now user matrix. So essentially think of this huge matrix consisting of M movies and U users, and you say that this can be reconstructed using a product of two matrices, M cross R and a R cross U matrix. So the M cross R matrix consists of M movies corresponding to H, which we learn some R factors, and then the R cross U matrix corresponds to the R affinities or R activations corresponding to the R features for the movies. And what we say is that this matrix can be reconstructed as a product of the M cross R and the R cross U matrix. And importantly, R is a much, much smaller number compared to M or U. That's why it's projecting the data to a low-dimensional subspace. And this problem is generally solved using alternative least squares, which is to say that you want to then basically if this matrix is A and you want to break this into, you write A is approximated as M multiplied with U. So you first fix M and then you learn U. In the next iteration you fix U and then you learn M. And this can be done using least squares, and you alternatively apply least squares. So that's how you can randomly initialize both the n cross r matrix and the u cross r matrix. And then the idea is to be able to accurately estimate the already existing numbers. And that's how you can define the objective. Again, I'm not going to go into details of the algorithm, but this was just to give you a glimpse of how matrix completion is a very beautiful algorithm. You can then again apply some different matrix completion algorithms to do something known as image in painting. So let's say if I want to make this picture less grainy and I want to in paint, let's say if there was some component which went missing, you want this to be completed. Of course, there are various really modern methods which do this same thing now, especially using GANs and other modern algorithms. But this has been studied since long time using more conventional algorithms also. And another interesting topic is to discover the graph structure. Let's say we have a set of random variables. In this case, you have random variables: gender, type of housing, education, age, IQ, some medical parameters, some social parameters. And across all of these parameters, you have a large data set. You want to construct a graph and you want to identify the graph structure. So again, there are some graphical models which you can leverage, and then you can build such connections. You can understand, you can estimate these weights. And this helps you to understand that, let's say, 22 and 25 are highly connected. So 22 is the treatment of your medicine and the satisfaction education. I don't know what these terms mean, but 3 and 28 are also highly connected. Age and age diagnosis, you would expect them to be connected. And 26 and 5 seem to be connected. 26 is work satisfaction, 5 is successful self-rating. So let's now talk about clustering in a little more detail. And just to revise, so the aim is to find some groups, subgroups or clusters in a data set. And we somehow need to define a notion of similarity. Like, how do we say that these two things are similar, or something should be within a cluster? So you need to have a notion of similarity. We have already discussed various notions of similarity when we were discussing k-nearest neighbor algorithm. So we just apply a similar sense of similarity to similarity here. And in terms of examples, so another important example which is highly leveraged is known as market segmentation. So this is how your telecom operators understand that, they'll identify that for college goers versus, let's say, retired people, they'll have different sort of plans, because they'll realize that this is a different market for each of them, and they'll segment the entire market, and then they'll accordingly sort of estimate what they can best offer to each customer. So here we see the iris dataset with the ground truth. It very naturally clusters it. You can see these 3 different clusters for these 3 different classes. In general, when we're talking about clustering, the first algorithm which is studied is known as k-means clustering. It's a very popular algorithm. We'll just introduce very quick set of terminology. We assume that we have n points in a d-dimensional space. We say that Ci is the set of points in the ith cluster. And then you would expect, this is an important property of clustering, that the union over all of these clustered sets is the set of all the points, as you would expect, because you want to cover the entire space. And the intersection between any 2 different clusters would be the empty set, because the point is uniquely identified in or assigned to each cluster. So what this says is that a point is unique to each cluster. Second, each point in this input data is assigned to some cluster. So this is some sample dataset which you can see that already seems to contain 5 different groups or 5 different clusters. But we could choose different amount of number of clusters, and we could end up with some different clusterings done. So let's say we didn't know that the number of clusters was 5. We didn't visually inspect the data. We kept k equal to 6. So So you see that this particular cluster, if you see, which was, you would usually expect this to be one cluster, but since you've mentioned that you want to do clustering with 6 clusters, one of the cluster breaks into 2 clusters. With k equal to 5, you get a fairly good clustering. K equal to 4, 2 of these clusters get combined and they're predicted or they're learned as one cluster. With k equal to 3, again, there'll be even more grouping of clusters that will happen. Let's take some examples of how clustering would occur, or rather, let's just first try to understand that what constitutes a good clustering, and then we'll go on to a demo to understand k-means even better. So I would want you to think for a second that what makes this a good clustering and makes this a bad clustering and this also a bad clustering. So if you already thought about this, you'd see that in this particular case, this cluster seems to be very widely spread. You can see that there are these points which seem to give a very large amount of spread. In fact, the question that I've asked was slightly loaded. So what I want you to say, what I want you to work in this is to first fix k, fix the number of clusters, and then look at different clusterings, and then tell which of them is the best. So unfortunately, I don't have an example right now to illustrate this, but the idea is that we want to choose a good clustering, and we say the clustering is good if the variation within the cluster is small. Like this particular cluster does not look like a very good cluster to all of us because we see that there's a huge amount of variation within this cluster. There are points which are really high on this dimension, and then there are points which are really high on the other dimension or low on the other dimension. So effectively what we want to do is to minimize the within cluster variance across all the clusters, right? So assuming k clusters, we want to minimize the sum of within cluster variance of ci, sum of the within cluster variance for each cluster ci, and you're basically looking at a joint c1 through ck that you're wanting to learn here, because once you change any ci, the others clusters are also going to be impacted because each of the point has to be assigned to one or the other cluster. And then we want to minimize this entire term as much as we can. Let's try and understand this term a little bit more. So we define the within cluster variance of a cluster ci as firstly you divide by the number of points in that cluster so that you get some average statistic, and because you don't want to penalize the clusters which have more points, they might naturally have more distance between them. And the other term that you want to write is the distance between all the pair of points. So that is the variance within a cluster. You calculate the variance, you calculate the distance between all pair of points, you divide it by the number of points. That's it. That's the simple definition of the within cluster variance. And you can mathematically write it as a double summation over each point A and each point B belonging to that cluster Ci, and you compute the distance between XA and XB. If you look at this notation, this is basically saying that you're computing the square of the L2 now. And we use this convention because X and XB are now vectors. They need not necessarily be scalars. And the cardinality of Ci is definitely telling you the number of points in Ci. Let's now come to the algorithm. It's a really simple algorithm. We'll walk through this. You can, in fact, let's just take a demo of this algorithm and then see. Okay, so we'll choose initial centroids and let's pick Gaussian mixture. Right. So what we want to do is to first we randomly assign the cluster centroids. So basically we say that this is the center point of one of the clusters and this is the other. So let's say we thought that this particular data set had only two clusters and we randomly initialize the centroids. The centroids are basically describing the one cluster. Once you've randomly done this, we then go. What happens is then you assign the set of points to a cluster centroid or to a cluster which are closest to it. So for example, all these points are closer to this blue centroid than to this red centroid. Thus, they're all marked as blue. And all these points which are shown in red are closer to the red centroid compared to the blue centroid. Thus, they're assigned the color or the cluster red. The next step is then to look at all the points which are marked blue and find the centroid of this data, and then look at all the points which are marked red and then find the centroid and then just update the centroid to these. So we'd expect that blue comes somewhere around here and red would probably come somewhere around here because we have some red here and some red here. Let's see. Yeah, as we expected. Now you repeat this procedure. You look at all the set of points and figure out which of them are closer to blue centroid. You assign all of them to blue, and the points which are closer to red, you assign them to red. You will see that once we do this step, these particular red points are definitely closer to the blue centroid compared to the red centroid, and then these will get assigned to the blue cluster. Okay, let's then update the centroids. You would expect the red one to only shift a little bit right because now it does not cater to these red points in the previous iteration, and blue one also to shift a little to the right, not much. So if you see there was some change. Now if you reassign the points, there will be basically no change. So you have now completed the optimization because you cannot change anything in the objective now. So you might have already seen that the sort of the cluster boundary which is learned is a linear cluster boundary between these two. Let's restart this. I'll use now 3 clusters. And just to show you the efficacy of k-means, when you're able to identify the correct number of clusters and the data is linearly separable, so in the form of the boundaries can be linearly separated, then let's say even if we choose some really bad initializations, right? So this is probably a really poor set of initialization. We would still be able to reach the correct solution. We definitely don't know which of them will be assigned which color. Of course, in this case, we can see that. But these colors by themselves have no significance until and unless a human being sits and identifies or gives some label to these clusters. If I click on go, now the first thing which happens is that each of the point gets assigned to a cluster centroid, which is closest to it. So we don't see any green cluster centroid yet. In the next step, we'll update the centroid. So you look at all the red points and you'll bring the red centroid to the centroid of these points, similar to the blue centroid to the center of these points. Once we do that, you now see that the red points which were over here are now probably closer to the green centroid compared to the blue and the red. So if we reassign points, all of these will remain red, all of these will remain blue, but some of these blue and some of these red should become green definitely. Right, that is the case. Now if we update the centroid, we would expect red to definitely move closer to this set of points, blue definitely move closer to this set of points, and green also to move definitely closer to the center. And that's what exactly happens. If we do the point reassigning now, these particular red points will be assigned to the green cluster now. And now you have sort of converged. If we look at some other data, let's say we take some max circles, let's say, and if we were to choose, let's say, 4 clusters. So if you keep on repeating this, you see that firstly the boundaries between them is as we discussed, are lines. So this cannot really capture some complicated patterns. So if we take some complicated pattern, let's say a smiley face. Now let's pick up this, this, let's say this, and let's see what clustering centroid it does. If you see, it gives you a fairly poor sort of clustering. You would have wanted this all these points in this particular space on this outer circle to be assigned to one cluster, eye in one cluster, the other eye in another cluster, and the mouth in another cluster. But this cannot happen because you see the boundaries that you learn between clusters are going to be straight lines. Of course, if we choose the same thing, let's say we explicitly sort of make it easier now, and we'll have to add, let's say, more points, and let's more cluster centroids. So again, you see that this for this case where the data is not really separable in the you cannot really choose a linear clustering. K-means is not a really good fit. There are other methods like spectral clustering which are definitely better suited for this application. So we look at the algorithm. In the demo that I showed, we first randomly chose the centroids and then assigned the points. You could start in the reverse order also, which is what I've written here. You randomly assign a cluster number I to every point. Then you find the centroid for a cluster Ci, and then you assign each observation to the cluster which is the closest. And you keep on doing this until convergence, until you don't see any change. Now I'm not going into the details, but this is known as the EM algorithm also, and this is guaranteed to give you a local optimum, but not guaranteed to give you a global optimum. So one thing which you do then to avoid this, to give you better chance of getting a global optima, is to reinitialize the first step or the first point when you randomly initialize the cluster centroids or the points assigned to each cluster. And if you do it enough number of times, there is a chance that you would get some better clustering where the objective is sort of better. And if you want to just very quickly understand the workings of k-means and where does the centroid suddenly come into play, the finer details you are expected to study on your own, especially while going through the EM algorithm workings. So let's assume that the centroid for the ith cluster is x point xa or xi, which is a t-dimensional point, and by definition this is 1 over the number of points in that cluster divided, which is multiplied by the sum of all the points in the d-dimensional space belonging to that cluster. Like that's how we define the centroid or the mean. We can rewrite this within cluster variance of Ci as 1 over Ci times just summation over the distances between all pair of points. And once you've defined the centroid, you can basically just repeat this and rewrite this expression as 2 times the summation of xa minus xi, where xi is the centroid. So this sort of gives you some better intuition as to how the centroid is related to this algorithm. Again, as I mentioned, finer details are in the EM algorithm, and it gives the local minima as we have discussed. Before we talk about hierarchical clustering, I wanted to show you some other examples of k-means clustering, again from the wonderful Python data science handbook by Jake van der Plas. And as you see that it is, so this explains the EM nature of the algorithm better. Yeah, so the first caveat is that expectation maximization or the k-means algorithm that we have studied will not give you, it's not guaranteed to give you a global optimum. So if you look at, now this has 4 clusters, but for k equal to 4, you could have a better clustering like this. This is the far worse clustering, and the way you can define this to be bad or worse compared to this, the earlier clustering, is using the within cluster variance formula. So the objective of this would be better compared to the objective of this. The second drawback or caveat is that you must specify the number of clusters beforehand. You That is typically not known. You can use various heuristics and methods to get a good sense of the number of clusters that you want to use. Again, you can refer to this article and look at silhouette analysis. There are other, of course, better methods, methods which don't really require you to specify the number of clusters. The other caveat, as we've discussed, is that k-means is fairly limited to linear cluster boundaries. For example, if we were to do k-means on this data, you would have ideally liked this to be one cluster and this to be another cluster, but that does not happen given the limitation of k-means. So it just learns a linear sort of a boundary. But if we were to use something like a spectral clustering, which uses the notion of graph of nearest neighbors to compute a high dimensional representation of data, then you're able to solve this. Then you're able to use k-means and solve this and get the appropriate cluster. And the final caveat is that k-means can be slow for a large number of samples. Thus, there are methods. To leverage that you don't. So basically, run it in batch mode or online mode, where you don't require the entire data to be loaded in memory at one point of time. The first example shows k-means on digits, which is you can go through. The second example is what is really interesting. I wanted to show that first. So let's say this is an image. Now, this is of size what? This is the 427 height, 640 width, and 3 color channels, RGB. Now, this consists of various of these colors, right? Various RGB pixels. Now, what we want to do is to figure out which are the important colors, or can we get the most representative few colors for this image, and then basically use a lesser number of colors to paint this image than the current number of total pixels, unique pixels being used. So I'll first show you the result, and then we can come back and see the final working. Right, so this is the original image, which consists of a lot of colors, right? But here what we have done is we've done some amount of color quantization, or we have effectively used 16 clusters on the set of colors in this image. So think of this as you have this original image, which consists of 427 rows, 640 columns. You just stack them all up, and you'll get what number? 273280 unique pixels, and corresponding to each pixels you have 3 dimensions, RGB. So think of it as you've now created a feature matrix X consisting of 273280 rows and 3 columns, and you're trying to now find the 16 clusters in them. So you basically now change the dimensionality, or you've been basically reduced the dimensionality from 273280 comma 3 to 16 comma 3. And for each of the pixel, then you look at the learned RGB cluster central and assign it to the closest color. And once you do that, you're able to then reconstruct, or just using 16 colors, you're able to get this output image. Of course, as the article mentions, that there are far better ways of compressing images, and you should look into the various encoding schemes. But this is something which now people have also taken up, that can they use machine learning to encode the images and the different color schemes. And finally, we look at the last topic in the last lecture of this course, which is hierarchical clustering. we said that one of the problems of k-means was that we needed to pre-specify the number of clusters. So what if we could get a clustering for all possible values of k? Let's just look at that. That is what hierarchical clustering allows you to do. The spelling of hierarchical is wrong here. So effectively, if we have to summarize this in one line, because of the gist of the name hierarchical, it gives you a clustering of all the clusters. So think of it as you keep on clustering different clusters. And we don't need to specify the number of clusters at the start. Let's just go through the algorithm and then we'll get a much better sense of hierarchical clustering. So you have an example data set. You have these points 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10, right? So initially you assume that each point is a single cluster, which makes sense. So you have 10 points. You can use 10 clusters, k equal to 10 clusters, and you will get this entire, each of them point being a unique cluster. The next step is to identify two closest points or two closest clusters, which we'll come to in a minute. Let's first identify them. So the point 2 and point 3 seem to be the closest. Okay, we have identified them. And then you merge these two, or you merge these two clusters. So each point is in fact now a cluster, if you remember. So now you merge the cluster 2 and 3. And then you keep on repeating this procedure. Let me just show you on the right hand side that what we have done, which is known as a dendrogram also. So if you figured out that the closest points were 2 and 3, right? So you looked at 2 and 3, and then you find out the distance between them. Let's say the distance between them is some 5 units or so, right? So you draw a line between 2 and 3 in such a fashion, or think of it as you've drawn a rectangle whose height is 5 units now, or whatever is the distance between 2 and 3, right? So this is now showing that 2 and 3 have been now merged, right? And then you repeat this procedure and identify the two closest points. Now, once you identify 2 and 3 and combine them into a new cluster, now that cluster itself can be compared to the other points. So maybe let's say that we represent each cluster by its centroid, right? And the centroid of 2 and 3 would be somewhere in between these two, right? And it turns out that that particular centroid is still closer to 4 compared to the pairwise distance between all the other clusters or points. So thus the cluster which was created using combining 2 and 3 is now combined with 4. And the distance between the centroid of 2 and 3 and point 4 and the fourth point is, let's say, somewhere around 10 units, right? So then you see that these points are going to be combining at a height of somewhere around 10 units. And then this whole structure will then again combine with, let's say, 1. So the centroid of 2, 3, 4 would be somewhere around here. That you will combine with 1, and that you will combine with 5 over these different heights. In fact, if you look on the other side also, 7 and 8 are also fairly close. So you can combine those, and the height of this dendrogram is the distance between them, which is somewhere around 10. So if you see 7 and 10 are somewhere around the height of 10. Then once you've combined them, you'll get a centroid which is somewhere around here. That you can combine with 10, then that you can combine to get a centroid somewhere around here. You can combine with 6, you'll get a centroid somewhere around here to combine with 9. And finally, this entire cluster and this entire cluster are also merged, which are now finally shown in this blue sort of lines. And the distance between them is, let's say, 45, 46 units, right? So this is essentially now the entire hierarchical clustering algorithm. And using this, you can now trivially find out the different number of clusters, right? So if you want to look at k equal to 1 cluster, so you just want a single cluster for all the points, which does not make sense. So then you cut this entire thing, this dendrogram, at the highest height, right? If you cut it at the highest height or above the highest height, all of the points belong to one cluster. You cut this dendrogram over here. So now you have split the data into two clusters. The first cluster is the point 5, 1, 4, 2, 3. The second cluster is the point 9, 6, 10, 7, 8, shown in red and shown in green. You can then again split it at another height, and then you'll see that you split 5 as one point and 1, 2, 3, 4 as one cluster, and you split 9 as one cluster and 8, 7, 6, 10 as another cluster, and you can keep on repeating this. And finally, if you go to the final height equal to 0, you have all the points as their own clusters. So using this hierarchical clustering, you can get the clustering for all the set of Ks. Of course, now this particular point that we said is that you identify the two closest points and merge them. So how do you identify that? So I said that we take the centroid of 2 and 3 as the new centroid of the cluster. But that's not the only definition of how you then compare. So do I compare 4 to the centroid of 2 and 3? Do I compare 4 with the closest point in this cluster meaning 2 and 3, the closest point is 4, or do I look at the farthest point, which is 2? These are just different ways in which you can define how to merge the clusters. And then there is a Google Colab link for the running this code. So with this, we end this particular lecture and we end this course. And all my best wishes to you.